Hello, this is Wil van der Aalst, and it's a great pleasure to talk more about, I think, two very interesting tools, Cortado and OCPQ. So OCPQ stands for Object-Centric Process Querying. And the bigger theme of what they will talk about today is that if you do process mining, it is very important to keep the human in the loop. Of course, with process mining, we want to support a data-driven approach. But what we see in many applications that is not enough. You need interaction with humans. Humans need, let's say, to query the data, to explore the data, then to discover models. Then they see models that they do not expect or they want to see something different. So there's a mixture of interaction, discovery, conformance checking. And in the end, the goal is, of course, that people better understand the processes and know what they need to do to improve them. So let's start with a bit of an overview, right? So this is the standard, let's say, overview if we introduce something like process mining. So there is a real world, and in this real world, there are processes, there are people, there are machines, there are products, there are files with information. And typically, this reality is being supported by software systems or information systems. The goal of process mining is to extract event data, let's say, from this reality and use these event data to get insights that are necessary to improve processes, sometimes completely automatic, but often it gives humans ideas on how they can intervene in problems. So the typical steps are you extract the data, you then explore the event data that you're looking at. Then if you're happy with the scoping of your data, you discover a process model that immediately provides insights in how you can improve the things that you see. Often these models are really surprising. Sometimes people already know that there are problems. In the next phase, once you have a clear idea of what you would like to see in reality, you start using more conformance checking, performance analysis, and these types of things. If you are a very mature organization and you have been applying process mining for some time, and your processes are under control, you can go to advanced topics where you are combining process mining with machine learning and AI to automatically intervene in your processes and to counteract, let's say, all the problems that you see. So this is a very broad overview. That's not what I would like to talk about today, but that is to provide a bit of the setting. The first let's say, topic that we'll talk about is querying. So querying event data is already something that is very challenging, but as process mining is moving from case-centric to object-centric, this is becoming increasingly important. So classical process mining is limited by the fact that you are just looking at a single process. You are fixed on a case notion. Even then it is difficult to query your data. But if you are dealing with object-centric data, where in some application you may be dealing with customers, with suppliers, with products, with orders consisting of multiple items, multiple shipments, per order there may be multiple invoices. So this is a real complicated reality that you cannot capture in a single case. Often, people are still reducing things to, let's say, a single case in such a way that you can apply classical process mining techniques. There is nothing wrong with that, but we are now moving to the next stage. So OCPQ is one of the tools. It was developed by Aaron Küsters, and he is a PhD in the Process and Data Science group at RWTH Aachen. The other tool that I would like to talk about is Cortado by Daniel Schuster. Daniel finished his PhD, let's say, last year. It is a very interesting PhD thesis because it combines different things that allow users to interact with process mining input and results. I will explain this in more detail later. As I mentioned, Daniel finished his PhD last year, and he now started, let's say, his own small process mining company. He provided the tool that is still case-centric, but makes it very interesting and easy to interact with process mining results, but also the input data. So this is the topic that we would like to look at today, and the unifying theme is, let's say, human in the loop. So both in querying and using tools like Cortado, there is this constant interaction between, let's say, people and the data, the models, in such a way that they get a better understanding of what is really going on. Okay, let's start with Cortado. As I said, developed by Daniel Schuster, where he was supported by several other people. Cortado, you may know that, is let's say, a type of coffee. I call it somewhere in between an espresso macchiato and a cappuccino. But in this case, it represents a very interesting process mining tool that allows interactions with the user. So this, let's say, slide is providing an overview. So normally if you do process discovery, you just load your event data, you push a button, and you discover a model. The only interaction that you have is that you may set a parameter. For example, I would like to filter out infrequent behavior. In Cortado, the types of interactions that you may have are much richer. So you decide on what are the trace variants that need to be included. You can also see that by including certain variants, your model, let's say, degenerates, and you will immediately see that. It is not only possible to select variants, it's also possible to select fragments of traces. There are multiple, let's say, ways in which you can inject domain knowledge, and the goal is that you use this domain knowledge to steer the discovery process. Because we all know this experience that if you just have a process discovery tool and you push a button, you often get like a process model that is reflecting the data, but it may be underfitting, or it may, let's say, also include behavior that you don't want to be included in the process model. Using Cortado, you can deal with these things. So one element is user guidance. The other element, which is very different from, let's say, traditional discovery, is that when you do discovery, you can again use the process model as input. And that's what you see here at the bottom. And so you don't start just from event data, you start from a process model, and you combine this event model, this process model with event data to get a better model. Note that in Cortado, you can also edit your process model. So you can change the process model and then seek immediately the confrontation with the event data, see which parts of the event data are then conflicting with how you would like to see the model. What you can also do is that you can, I don't know, discover a process model based on the frequent variants. And then after having, let's say, the core model, you start adding, let's say, different variants one by one. And in such a way, you are extending your process model in a controlled way. In all of these phases, it's very important to visualize both the process model, but also the different variants that you're looking at. And Cortado is doing precisely that. So if you look at the PhD thesis of Daniel, you will see, let's say, this taxonomy. I do not want to expand on this too much, but it is basically talking about these non-trivial forms of process discovery, where you are using an existing model, or you're injecting domain knowledge, or you make it very, let's say, easy for users to kind of, let's say, cut out the parts of the event data that you would like to be used for discovery. What you can also see here is that there are many possible dimensions. You can look at declarative models, at imperative models like BPMN, Petri nets, process trees, etc. You can also look at the time where you want to introduce domain knowledge. So do you want to do it before you do discovery, while you are doing discovery, or afterwards? So there are several techniques for, let's say, model repair based on event data, where you typically have a model and try to inject domain knowledge, let's say, at the very end, after you already have the model. So this is the spectrum, and Cortado is trying to support this as good as possible. And this is like a screenshot of what the tool looks like. So what you see here at the bottom are the so-called variants, and based on these variants, you can discover process models. So what you see here at the top is a process model expressed in terms of a process tree. And let me, let's say, point to different parts for people not familiar with process trees. So this is a sequence. So this is a process that is intended to be funny, right? So it is about, let's say, creating pizzas and then eating them or not. So this is a process tree. It's a hierarchical description of behavior. You can also, in Cortado, view your processes in terms of the BPMN notation. I will show that later. But this is what is used internally as a representation. So it's also important, if you would like to understand the tool and how it works, to also look at this visualization. So, as I said, the process model that has been discovered here on these traces starts with creating a pizza base. It ends with cleaning the kitchen. In between, there are these two sub-processes. So in this sub-process, before clean kitchen, we either do nothing, right? That's represented by let's say, the empty activity, always named tau by convention. And the X means a choice. So here we have the choice between doing nothing or eating the pizza. In this sub-process, we are, let's say, looking at concurrency. So there is no ordering relationship. Things happen independent of each other. So we can add cheese or not. We can add tomato or not. And we can add salami or not. There is not a fixed order. And all of these toppings are, let's say, optional. So I can create a pizza with just cheese on it. But I can also create a pizza with tomato and salami on top of it. And at the end, I'm either eating the pizza or immediately go clean the kitchen without eating it. So to show the whole data being used here in Cortado, like I can increase, let's say, the lower part of the screen. So what you now see is you see all the, let's say, different variants. You see that some are very frequent. So at the top, you see, let's say, almost 5,000 variants. If you go to the bottom, for example, the last one is only happening, let's say, 27 times. So this is the data that is used as input, and you can clearly see it's case-centric. So in total, I believe we have 2,000 cases. And for every case, we have a sequence of activities. So in the model that we were just looking at on the previous slide, this is basically discovered on the whole data set. So what Cortado allows you is not to just discover a model based on the whole data, but I can now also look at the successful executions of this process. So here I'm now focusing on all the activities where we are actually eating the pizza. Let's call that a success. So we look at these 6 variants. So the ones with the arrows that have a length of 6 activities happening in a particular sequence. These are all the executions where we are eating the pizza. Note that we have 3 toppings. So in total, there are 3 times 2 times 1. So 3 faculty possible combinations of that. If we select these, as you can see here, we can say discover the initial model, and then we find this model. So this model is by selecting the successful executions. And this looks, let's say, very, let's say, convincing, because we get exactly the behavior that we want. So we start with pizza base, at the end we do eat pizza followed by clean kitchen. And before eating the pizza, we add the 3 toppings, but this can happen, let's say, in these 6 possible ways. So we can first add cheese, then salami, then tomato, and in total there are these 6 possibilities. So that's the, let's say, the model that we discover based on these successful executions. At any point in time, you can click on editors and you can also have a BPMN view. So this will be, let's say, more familiar to many of you. So we start with pizza base, then we add the 3 toppings. It can happen in any order. Then we eat the pizza and then we clean the kitchen. This is typically much easier to understand. But in the internal computations, in the background, always, let's say, process trees are being used. So what I now could do to show other capabilities of Cortado, I could select these 2 variants, right? So pizza base, add tomato, add cheese, clean kitchen, and pizza base followed by add cheese, add tomato, and clean kitchen. So I add these 2 variants next to the model that we already have. And now I can say add the variants to the model, and then the model is extended. So we take as input a model and these 2 extra traces, and we create a model that allows for this behavior. So at first glance, this looks very good, right? Because now in all of our data, we always add cheese and add tomato. There's not a fixed order. Add salami is optional because we have these 2 variants where we are not adding any salami. And the pizza has become optional because in these 2 variants that we selected, we are no longer eating the pizza. So this model looks good, but it's also imprecise because this allows, for example, to add cheese and add tomato and then eat the pizza. And we never have seen that behavior in the data. It's also possible that I add all 3 toppings, also salami, and in the end, I'm not eating the pizza because I'm choosing this branch where I skip eat pizza. So the model allows for much more behavior than what we have seen in the data, but it is guaranteed to allow for the original behavior in the model and the new, let's say, 2 variants that we have added. What you can always do is you can go back and interact with, let's say, this model in a different way. So now I took a step back, and now I would like to use a different approach where I want to freeze this part of the model. And freezing a model basically means, so you select this subtree, and then you click this button, and you're basically freezing it. That means that you want to protect that part of the model. So you're selecting a part of the model that you don't want to disappear. And you want it to be included. And then after I freezing this, right, then it turns blue, I can again add the 2 variants that I looked at before. And if I do that, it is guaranteed that this part will return. And if I do that, actually I get a much better model, right? So now in this model we have pizza base in the end is followed by clean kitchen, and we have the scenario where we eat the pizza and all 3 toppings have been added, and we have the scenario where we added tomato and cheese but no salami, and therefore we were not eating the pizza. So this is a very precise model, exactly capturing the behavior that we had seen before. So this is very, let's say, elegant. What we can now do is that we can add also the rest of the traces. So now if you click here, you can select, let's say, all the behavior. I add all of them. And if I do that, then we get this model. So in blue, again, you can see the part that we had frozen, that we wanted to protect. So we wanted to protect this subtree. And like if things do not fit here, then it has to be added as extra behavior. In the background, things like alignments and lots of, let's say, computations are being done to decide what to do precisely. So if I unfreeze it, then you can better, let's say, see the process model. So you have the scenario where you're eating the pizza, you added all 3 toppings, so this is corresponding to 6 variants. And you have these other variants where in the end you are not eating the pizza, and because like not all the toppings are there. So this is I think a quite nice model capturing the behavior of what we have seen in the data. As I mentioned, at any point in time, it is possible to discover, so to visualize the discovered process tree as a BPMN model. So this is what it looks like in BPMN. So after creating pizza base, there's the possibility that we do nothing and immediately go and clean the kitchen. There is the possibility that we add all 3 toppings and eat the pizza, or there is this possibility where we are adding the toppings, but in the end not eating the pizza. So very few discovery techniques, if any, are able to discover this model, because what you note is that the activities are occurring multiple times in the model itself. And this is very difficult for automated discovery techniques to do, but with the freezing we could realize this. So this is showing, let's say, this corresponding. So here we have the data, here we have the model, and like this is actually the model that we would like to see based on this data. I just showed you a very tiny fraction of the capabilities of Cortado, but I hope that this makes you interested in the tool itself and this notion of interactive incremental process discovery. There are many more features. So for example, you can also have these higher level variants where you're, for example, capturing when activities are taking time that they are overlapping, right? And based on this, like there are all kinds of, let's say, novel interactions with the user. Something that I did not mention is that at any point in time you can do conformance checking. It's highly interactive, and you see exactly, let's say, diagnostics where the model is not supporting some of the data that you've seen before. There is this, let's say, tool paper in SoftwareX that you can read if you would like to see more details. And there is also this GitHub site created by Daniel, where you can download the Cortado tool, right? There is also a build for Windows, so it's super easy, let's say, to install and to start using it. So after this, I hope you got interested, and let's take a look at the demo. So I just started the Cortado tool. What you can still see is an old project where I discovered, let's say, a model based on the event data that we see below. But let's start with a very simple example. It's the example of, let's say, creating pizza processes. So you can load XCS files. So Cortado is a case-centric tool. Now you see the old model, but for example, one of the things that I can do is that I can, I don't know, select all the variants and discover an initial model. There are 2 types of visualizations. There is this visualization, which shows a BPMN model, but there is the other visualization that is used in the background where, let's say, a process tree is being used. So if we select all the variants, right, then this is the process model that we get. But let us first look in a bit more detail at the data. So what I do here is that I've loaded, like I visualize now all the variants. Let me expand them so that you can see the full names. So what you now see is that in total there are 16 variants. You can also see the frequency. So for example, the first variant is happening 494 times. The least frequent variant is happening 27 times. So what you see, this is intentionally a very simple process so that you can kind of still, let's say, see the relationship between the models and the data. So the process always starts with creating a pizza base. At the end, we always have the purple activity clean kitchen. And between pizza base and clean kitchen, there are other activities. And what you perhaps see is that there are these green activities, eat pizza, and the other three colors, yellow, blue, and red, correspond to adding the toppings. There's also this variant, which let's say means that we basically do nothing. This is leading to a fall through. So if I say discover the initial model, switching all of these things on, right? I just did, and I look at the process tree. Then because we had the empty, let's say, pizza base immediately followed by clean kitchen, we have this choice here. So due to elegance, let me go back and remove this variant and let's say discover again an initial model, make it smaller. So what you now see is that this fall through has been removed. But let's first take a look at the example. So this example, if we do a conformance check, is fitting the complete data. And note that there is here a button conformance check. So we can do a conformance check, and it already computed that all of the 2000 instances are all fitting, right? There are 2000 cases and there are 16 variants. To be familiar with this process tree notation, so what we see is we have a sequence here. It always starts with pizza base, it always ends with clean kitchen. At the end, there can be an eat pizza activity before clean kitchen, but it is optional. So this cross means that it's a choice, and this tau, these smaller activities with the tau in them, they are corresponding to, let's say, skipping, doing nothing. So it shows that we have pizza base, this part in the middle, and then we may eat a pizza or not, and then we clean the kitchen. This is an AND. Right? So this means that after pizza base, concurrently, there is no fixed ordering between these three subprocesses. And in each of these subprocesses, we can add a topping or not. So there's a choice between doing nothing or add cheese, the choice between doing nothing, add tomato, a choice between doing nothing and add salami, and this part can be done in any order. So what we can clearly see, conformance checking also supported this. This is completely supporting, describing so all the traces, all the variants in the event log are possible. And as I mentioned, at any point in time, I can switch to a BPMN view, and this is probably more readable, let's say, for most of you, right? So we have pizza base. Then concurrently, we have adding the toppings, but we can bypass each of the adding activities. Then we synchronize here, and then we do nothing, or we eat a pizza. So this is, let's say, the model that we would get using, let's say standard discovery. So if I say discover initial model, we are, let's say, using the inductive mining algorithm by Sander Leemans, what is used in the background without any noise filtering. Let me switch back to the process tree view because it's important that you are familiar with this. So this process allows for that you skip all the adding activities and then in the end eat the pizza. That's clearly a variant that we did not see. So we can eat a pizza without any toppings on it. That was not supported by the data. We can also add all of the toppings and then not eat the pizza and clean the kitchen. And so if I now look at the data again in more detail, right, what you can see is that the model that I just showed is able to describe all of these variants, but also many more. And so what we see in the data is that eat pizza does only happen if all three toppings have been added, right? If one of the toppings is missing, so for example, we just have salami and cheese and no tomato, we do not eat the pizza and clean the kitchen. So this is not captured, let's say, by standard discovery techniques, because this requires, if you want to model this properly, that you have, let's say, multiple activities with the same label. Let's now show this interaction a bit more. Let me unselect all of them. And now I'm just selecting the successful cases, the successful variants, where we are actually eating the pizza. So I selected these 6 variants. So note that they are corresponding to adding all 3 toppings and then eating the pizza. Because there are 3 toppings, they can be ordered in 6 ways. For the first one, we have a choice of 3. For the second topping, we have a choice out of 2. For the last one, we don't have any choice. So it's 3 times 2 times 1. In other words, 3 faculty. That is explaining why we have 6 variants. So based on this, we can discover an initial model. And if I kind of show that in a bit more detail, it looks very elegant, right? So we have pizza base, we always eat the pizza, we always add all 3 toppings, but all orderings are allowed. And then at the end we clean the kitchen. So this describes precisely the 6 variants that I just selected. So let's now show another capability, because what I so far showed is just like selecting variants and then discovering a model. Suppose that we would like now to add variants without recomputing the complete model. So we would now like to take this model and repair the model in order to allow for this behavior where we add tomato and add cheese, and I take both orderings deliberately. And if I add these variants to the model, we get this process. Right, so what we now have is kind of what one would expect if one would do discovery. So pizza base at the beginning, clean kitchen at the end. And now for these 2 variants, we need to skip eat pizza. But in all of the variants that we have selected, we still add cheese and tomato. But adding salami is optional, right? Because it's not happening in these 2 variants that I added later. So now we have this model. But this model is not, let's say, so good, because what it kind of destroyed the structure that we could see before. Let me go back. If I go back one step. So we had this structure before where, like we had eat pizza and after adding all of the 3 toppings. So this is lost if we apply the approach that we just said. Because it allows you to eat a pizza where salami is missing, right? Which is not supported by the data. And so we can eat a pizza without salami, which was not in the data. And also, if we add all 3 toppings, we may skip eating the pizza, right? So it doesn't correspond to the data. Let me now show another capability that nicely shows the type of interactions that you can have. So you can freeze parts of the tree, right? I select this node and I say that I want to freeze it. So what does freezing like a subtree mean? It means that the behavior that is described in the subtree needs to be preserved. So this is like a process fragment that whatever you do, the discovery technique can do whatever it wants, but this structure needs to reappear. So this allows us for all so if we are computing alignment, for example, we can see, let's say, the parts that are not fitting. And instead of, let's say, destroying this nice structure, we can add other optional structures. And let me now again add these 2 variants that so we are doing exactly the same as what I did before, but I now freeze this subtree colored in blue. We again add these 2 variants, and now we get this model. So what we now see, if I make it a bit smaller, right? So what we now see is that we preserve like this nice structure that after we added all the 3 toppings, we eat a pizza. But at the same time, the 2 variants that we added all have this behavior where we add cheese and tomato in any order and skip eating the pizza. Right? So this is a perfect model describing exactly the things that we would like to see. If I now do a conformance check, of course, there are, let's say, variants that are not fitting, right? They are highlighted here in red. And so you can see that half of the variants are not fitting. So now we would like to retain this precise part of the model and at the same time allow for all the behavior. So what I now can do is that I can freeze this entire tree, right? So we would like to preserve this behavior. And what we now do is we select all the traces and then we add these variants to the model while freezing this part of the model. And then we get this structure, which is very, let's say, nice, because what we now see is that we still have, it always starts with pizza base and ends with clean kitchen. We have this tree in blue that we have frozen, right? So it's guaranteed that it remains part of the model. And here we have all these behaviors where, let's say, we are not eating the pizza. So if I now, let's say, unfreeze this part, right, now you can see the colors, and now you also see that, for example, add cheese is happening twice, right? And using a normal discovery technique, that would never be possible. So we have a fully fitting model that is much more precise than the model that we had seen before. Right, I can make it a bit smaller, the bottom part, so that you can better see it, right? And it also nicely illustrates, let's say, the notion of process trees. I can, again, of course, show the BPMN view, and then it looks like this. And so we start with pizza base, clean kitchen. We either do nothing. We have this scenario where we add all 3 toppings and then eat the pizza. And we have these, let's say, behaviors where we are forgetting, let's say, to add a topping. So now you can see that the model is much more precise than the model that we got in the beginning, where we were simply selecting the traces and discovering the whole model. Right? I can show that to you again. Right? So if we now discover again an initial model, we now see that again we have this. So if we discover from scratch without freezing, interacting with the data, then we can see that we can again eat a pizza without any toppings. So we have all the problems that we have seen before. So hopefully this illustrates, let's say the capabilities of Cortado. Of course, I do not do justice to it because, like, there are many more capabilities. And so, for example, it also allows for variance, where you are, let's say, considering the fact that things are overlapping, right? I can also, let's say, for example, play with time granularity, and then you see that illustrated a bit. So now all the, let's say, activities that are happening within the same time period are, let's say, put, let's say, concurrent to each other, because this data set only has starts or just completes, just what you, the way that you view it. And they're just atomic activities, like this is not so useful, but you get an idea of like how it is also able to use trace variants where like concurrency is kind of explicit, and based on such variants you can also always, for example, discover a model using this concurrency, right? So now we get something that is, let's say, underfitting because of the modifications that I made, that we no longer see that it starts with pizza base, because pizza base is concurrent to many other activities. Just to show, right? Also, you can always click the documentation button, and then you can, let's say, read, let's say, about the various things. There is also things like a query language. You can do pattern mining. You can do let's say, clustering. There are lots of capabilities that I did not show that you can by looking at this help page that you can easily see. So this concludes, let's say, the short explanation of Cortado. As I mentioned, this is a tool that is mostly developed by Daniel Schuster. I think it's a remarkable, let's say, PSD project where like all the different techniques that he worked on have all been integrated in a single tool that really, let's say, encourages user interaction. So in this second part, I would like to focus on object-centric process querying, and for that I need to give a crash course in object-centric process mining. In Cortado, we were focusing on case-centric event data. Now we are focusing on object-centric event data. So in case-centric event data, every event is corresponding to a case, an activity, and a timestamp. Right? This is classical. And what we could see in Cortado, we can use the timestamps to order things like in a linear sequence. If for activities we also take the start and end, we may see that things are overlapping and it becomes more like a partial order. But it always talks about an event referring to precisely one case. So this is traditional. However, we have seen that this worldview is very limiting, because in reality, an event may refer to many different types of objects. So if I place an order, it may refer to a customer, to the order that is being created, to the items that are being ordered, and there may be many more objects involved. And we look in production, and we are, for example, assembling a component from smaller components. It's clear that the case notion is not so easy. If you would go to a hospital, there is not just a patient, there is also a doctor, there are nurses, there are blood samples, there are X-ray machines, right? So reality is not so simple. You can reduce it using a case notion to something very simple, but you're often leaving out things. So that's why object-centric process mining is like becoming, let's say, the norm. My favorite example is, for example, how Lufthansa is using process mining to reduce delays. And if you think about a plane landing, for example, in Frankfurt, or a plane landing in Munich, many things are happening involving many different objects. And so if a plane lands, you need to offload all the suitcases before you load new suitcases. And so you have suitcases as objects. There are the passengers that need to leave the plane, but also there are new passengers that are, let's say, boarding the plane. So passengers are an object type. The plane may need to be refueled, right? And this is involving equipment that needs to be there. And I could go on and on and on. There is also, let's say, crew that is first standing at the check-in desk and is later standing at the gate. So there are all these objects and all these different events that are connected to each other. So to look at a simple example, this kind of the classical example always used is that you can think of, for example, orders consisting of items, and these items are delivered in packages. In one order, there can be multiple items. One item is always in one order. An order may also contain just one item, but in this example, both orders consist of 3 items. There are also 3 packages. And so, for example, if I look at the last order, these 2 items were delivered in the same package. But if you look at this package, then you see that this package contains an item from the first order, this iPhone, and this controller from the second order. This package is containing 2 items, let's say, from the first order. So there is a many-to-many relationship between orders and packages, and there is a one-to-many relationship between items and orders and items and packages. I think you get the hang of it. So this is a reality, right? So we talk about object types. In this example, we have orders, items, and packages. So We had 2 orders, we had 6 items, and we had 3 packages. We also have these activities, like things like place order, pay the order, pick the item from the warehouse, reorder it if it's not in stock, and in the end there are things like delivering the package. Note that this is like a highly simplified example showing the concept of object-centric event data. So in technical terms, we talk about object-to-object relationships and event-to-object relationships. So the red lines here are corresponding to event-to-object relationships. So for example, activity place order involves orders, 1 in this example, and is involving items, and here there can be multiple items involved in the same order. If we look at, for example, package delivered, it corresponds to a package and to the items that are inside this package. The O2O relationships are modeling the fact that an order may consist of multiple items and a package may consist of multiple items. That type of data has been standardized. There is the so-called OCL 2.0 standard. At the bottom you see a URL. And this is, let's say, the de facto standard at this point in time to store such data. If you look at this model, and I do not want to explain it in detail, but it's important that you know that it exists. So we have events, and events are typed. We typically call that activities. We have objects, and objects also have a type. There may be these object-to-object relationships, and there may be these event-to-object relationships. These relationships may be qualified, and both events and objects may have attributes, and of course these attributes have values. Events also have a timestamp, and object attributes may change. That's why you also see this connection here. It's not important, it's just that you get that you are aware that these things exist. If you would apply classical process discovery, what you would see is that you would see, okay, we can discover the flow for orders, we can discover the flow for items, and we can discover the flow for packages. This is using traditional process mining. But the step before this is that I have flattened my event data. And so look at, for example, place order. There were 2,000 orders, so 2,000 times an order was placed. But because an order may consist of multiple items, in this example on average approximately 4, we see here that place order happens 8,000 times, right? Because we are tracking items instead of orders. So you can see that the same place order event is replicated here for every item in it. Here in total there are almost 1,300 packages. Like here is a nice sequence if you focus at the package. However, if you look here at package delivered, you can see that it happens 8,000 times. But there were only these almost 1,300 packages. And again, we have replicated here events in order to describe the flow of the different items. So in object-centric process mining, you try to avoid, let's say, these problems, right? You want to have one integrated model, and you do not want to see these distortions. The distortions that I'm highlighting here are called convergence. That means that something that happened only once is replicated multiple times, leading to misleading diagnostics. There are also other, let's say, problems like divergence, but it is not the talk to expand on this in detail. In general, these distortions are a real issue. The way to handle this is that you kind of bring data back and you go back to the original frequencies. For that, you need to have so-called variable arcs that you see in this example, and then you can fold the different, let's say, flows of objects into one integrated model. So this kind of picture reflects the idea of object-centric process discovery. You would like to discover one model that is describing multiple types of objects and also their interaction with each other. This is not the topic of this talk, but it's important to understand why object centricity is so important. From a practical point of view, there are three main advantages. The first advantage is that using object-centric process mining, you no longer have to go back to your source systems. That's an important, let's say, a factor. Before, if you use case-centric process mining, each time you change your question, you may need a new case notion, and you need to go back to your source systems and extract the data again. The second, let's say, problem that object-centric process mining is trying to address are these problems like convergence and divergence. And I did not explain this clearly enough, but you have to believe me that if you are flattening your data to be case-centric, in that process, you're kind of distorting things, right? The same as if you're trying to compress a 3D image in a 2D image, like you can say it's not wrong, but it may be misleading, right? Because you cannot see, let's say, the third dimension anymore. Here we have simple things like that frequencies of activities are incorrect, or if you see, for example, an average time between two activities, it is not so clear what it means, right? And using object centricity, you can address these problems. Finally, most of the problems that we find in processes are not, let's say, restricted to a single object type. You typically need to look at multiple object types at the same time to find the root cause of problems. And so in the example that I just sketched, we would like to measure the time between when is an order placed and when is the last item in that order actually delivered. And that requires that we go from orders to items to packages, and we look at what was the last package delivered still containing items of the order that was placed at a particular point in time. So these are the main advantages. So sorry for this long, let's say, introduction, but this is like basically motivating why object-centric event data are very important, and existing querying notions for case-centric event data have difficulties dealing with this object-centric, let's say, process data. Let alone if you're using something like SQL, right? And it's even more difficult, right? Because then it's not process-centric, and asking questions about the data is very difficult. So Aaron Küsters, and he started working on this in his master thesis. He's now doing a PhD, developed a tool and approach, a language you could say, which is called Object-Centric Process Querying. And I think it's a beautiful, let's say, approach that is more understandable than existing approaches, and it's also much faster than existing approaches. So the motivation is that querying object-centric event data is already very challenging, but querying object-centric event data is even much more complicated, right? Because you're dealing with multiple object types, and I hope that the example that I just gave you gives you an idea. So an interesting observation is that if you look at querying and checking constraints, they are very much related. And as an example, I'm using here the Disco tool. So Disco is not supporting conformance checking, like that you give a process model and that you check whether the data fits the model. What you do if you want to do conformance checking using the Disco tool by Fluxicon, what you need to do is that you set a filter. And by setting a filter, you may basically look at what are violations, and if the filter says, okay, I find no cases satisfying these conditions, then you do not find any violating cases. And so, for example, you can set a filter that you say, I'm interested in cases that take longer than 5 weeks. If there are no such cases, then that conformance constraint is satisfied. The same as if you want A always to be followed by B, you can basically look at the negation and then check whether that is empty or not if you're doing querying. I hope that you get the idea, right? That query and constraint checking are very much related. The inspiration for object-centric process querying came through, let's say, the Z notation. So something when I was doing like my master thesis, like that was a popular language at that point in time used for specification. And we borrowed some concepts, let's say, from that language. So you can explicitly declare variables, you can describe constraints over these variables, and very important, you can extend a Z schema with another schema, right? So this add birthday schema is using the birthday book schema. So we are using this kind of schema-like notation, explicit introduction of variables, constraints over these variables, and then like we allow for a nested structure. So the Z notation has been around for a very long time. It's also an official ISO standard, but today I think very few people are familiar with it. But as you can see, it works very well in this domain to use this style. So this is an example, let's say, from the first paper, let's say, describing this OCPQ language. So this visual representation here is describing the following constraint. If a third payment reminder for an order is sent to a customer, no other order by this customer, that's very important, should be confirmed afterwards. So in natural language, at first this sounds very simple, but it's actually a very complicated query. So here, this is described, let's say, visually. You do not know the concept yet, but I will walk you a bit through it in such a way that you kind of get a bit of a feeling how this works. So O1 is an object referring to an arbitrary customer. O2 is an object, so it's a variable for an object referring to any order. Then we have an event variable, E1 is referring to payment reminder. And then we set the filters, because like these things now need to be combined. So there is an O to O relationship between customer and order. So we are interested in the orders belonging to particular customers. And so if we now look at O1 and O2, we see this combination, we know that this customer placed this order. Also, E1 is related to O2 through an E2O relationship. I explained this earlier. And now I look at the combination of these two things. So we look at the payment reminder for this particular order. So this is what we see in this part. Now we go to the lower part. So here we look at payment reminders. And when you have this connection, basically the variables and the filters still apply here. So what you now see is here E2 payment reminder is introduced. It's a different variable than here. This payment reminder has to come from the same order. So that's one filter. The other filter, like this one, is describing that E2 should be followed. So we look at the difference between E1 and E2, and this should be negative or 0. That means that E2 is happening before E1 or at the same time of E1. So with E2, we are basically ranging over payment reminders, not after E1, but before E1, including E1 itself. So that's what we write down here. And this is connected through this A structure. And here it says that the size of A should be at least 3. So if we look at the combination of, let's say, customer order and payment reminder, and then we navigate to these payment reminders that were happening before, including E1 itself, there should be at least 3. right? So here we set a filter and we are looking at this combination of customer order and payment reminder where there were already 3 payment reminders. And now we go to this by this customer, right? Because we did not really use, let's say, 01 yet. So what we do here is that we look at orders and we are looking at all the orders that are connected to 01, which is the customer. We look at the confirm order, the confirm orders that are belonging to the order. So we are now looking at an event confirm order related to 03. And again here we are looking at E1 is followed by E2, and this should be 0 or larger. Right, so here we are looking at, let's say, events that are happening after the time of payment reminder. Here we were looking at events before, let's say, this last payment reminder. And now, so this is what is undesirable. And now we write a constraint, so b is equal to 0. So given this combination of customer orders and payment reminder, we don't want there to be any children, so any orders that have a confirm order after, let's say, this time of E1. So that's what you see here. And now you also realize that in natural language this looks very easy, but it's actually there are lots of the hidden design choices and things that are not clear from the sentence at all. But this is the way that it looks in object-centric process querying. So if we load a data set in this tool, it looks like this. And so this is like a publicly available data set from, let's say, the OCL standard website. So there are 21,000 events, 10,000 objects. These are the event types, these are the object types. Like using OCPQ, you can, let's say, explore this. So you can look at an object or event, and then you can look at its neighbors. And so here you can now see this graph-like structure of the data. I can also zoom in. And so this was the graph that I got it by looking at this order. And you can see that this order is connected to specific events. And it's connected, let's say, to let's say, certain items and products, etc. So this whole data set, although it's relatively small, let's say, for our kind of applications, for, let's say, explaining and demoing it, let's focus on just orders and items, right? So we have orders and items. You can see the variables that they have. These are the event types corresponding to orders. So you have place order, pay order, etc. And events have many more, let's say, possible, so items have many more possible event types related to them. And again, you can also see the frequencies. So hopefully you get a bit of a feeling for the data. And in OCPQ, I can, let's say, describe something like this, right? So we have a variable orders, we have a variable items. We look at an event place order, an event package delivered, and now we relate these things, because if there would not be a filter, we would look at all combinations of all orders, all items, all place order events, and all package delivered events, right? That would be in the many millions if we would do that. But we set a filter that like this place order event should be related to this order. This package delivered event should be related to this item. And like 01 is related to 02. So it is an item that belongs to this particular order. And now I write a constraint, and I'm looking. So for all the combinations of orders, items, place order events, and package delivered events, of all of these, in total there are 8,000 of them, we look at the following constraint, that E1 should be followed by E2 within 4 weeks. And so within 4 weeks, we should E1 is followed by E2. And this is almost always satisfied. That's why the box is green. And so in 3%, this is violated. So that is corresponding to, let's say, a bit more than 200 combinations of these attributes. So these are the violations. And so in very briefly in natural language, you could say 3% of the items are delivered too late. We can click on this number and then we see, let's say, all these almost 8,000, let's say, combinations of O1 variable, O2 variable, E1 variable, and E2 variable. Right, and we can see the violations or not. We can also click on this, and then this table that I just mentioned with almost 8,000 rows is then filtered on all violating cases. So now we see the 236 violating cases. And it's important to see that because we have these 4 variables here, like we have a table with these columns for each of these variables. Let's make it a bit more complicated, right? And then you get an idea of like you can basically describe any query. So what we have at the top, we have O1 are orders, E1 is place order, and place order should belong, so an E2O relationship between a place order and orders. So there are 2,000 orders, they all have one place order event, so the frequency is 2,000. Now we look at these, let's say, boxes, and they basically inherit everything on the path to the root. So if we look at this one, we add O2, but O1 and E1 are still available in this context. We add here items, and we add E2 as an item out of stock event. E2 is related to items, and O1 is related to O2, right? So here we had an order, here we have items. So we are considering here the items that belong to this order. And these items have an out of stock event. What we see is that this, like if we would look at the table behind this, it has over 1,500 rows. And right, we are not using that yet, right? But this is to show that the context that we have here is basically copied in here, and we can add more variables, but also set more filters. On this side, we look at also at items. These items are connected again to the order using an O2O relationship, and now we go one level deeper, right, where we look at failed deliveries, and these failed deliveries should be related to these items, right? And what we now see is that there are in total 2,020 failed deliveries. So note that I'm not using these variables A, B, and C yet, but it is just showing like we are copying the context, right? So in this context that we have here, we do not just have E2, we also have O2, and we have O1 and E1, right? So all of these things are available here. Now let's start using these variables that you see on the arc. So we can use that in filters and we can use that in constraints. So here I'm saying that C should be at least 2. So you can think of this as the children of this row, right? So every box is corresponding to a number of rows. In this example, almost 500. And we are interested in the rows that have at least 2 children. And these children are basically extending it with failed delivery. So what this is expressing is that 468 items had at least 2 failed deliveries. And so before they were delivered, there were 2 attempts to deliver that were unsuccessful. So here you can see how we can use these child boxes in the parent box. focusing on things like cardinalities, etc. We can also, let's say, use this C variable in the constraint part, right? So what we now see is we did not add it as a filter, we added it as a constraint. So again, here we see all the items, almost 8,000. And what we are now saying is that in the constraint part, C should be 1 or 0, right? So that's the constraint. So for every item, the value C should be 1 or 0. And so we allow for 1 failed delivery, but we do not allow for 2 failed deliveries. So this is violated in 6% of the cases. That means of these 8,000 items, almost 500 had multiple failed deliveries. And so at least 3 attempts were necessary to deliver, let's say, the item to the customer. And again, we can, let's say, click on any of these numbers and see the cases that are underneath it. In this part of the model, again, I moved, let's say, this C upwards, right? I didn't add it as a constraint, but here we are interested in, let's say, items that had multiple failed deliveries. So you can have 1, but if there are multiple, right, it pops up here. So here in total, almost 3,000 items had multiple failed deliveries. And like if you now see, we are now using, so we are using C here, we are using A here, and we are using B here in the constraint part. So here we are filtering on, let's say, orders and place order events in such a way that there are, let's say, 1 more out of stock events, right? So we look here at an order, we go here to the items, and we are interested in orders that had items in them with, let's say, at least 1 item out of stock event. So that's what the filter says. The constraint then says that B should be smaller than 1. And remember what this part was. So we had these 300 items that had, let's say, multiple failed deliveries. And now we are interested in, it is okay that an order has 1 of such items that had multiple failed deliveries, but now like an order cannot have multiple, or an order should not have multiple items that have multiple failed deliveries. That's what we're describing here. And note that there are these 3 levels, right? So we have order, we have the items, and we have, let's say, the failed deliveries, right? The packages that we try to bring to people's home. We see that 6% of the orders having an item out of stock have multiple failed deliveries. And this is the constraint that you see here. So this is a bit artificial, but kind of by just focusing on these 2 object types and just a few activities, this was the easiest way to illustrate this a bit. So here you can see another constraint. It says that it's based on a different data set about people applying for jobs. It says that after an application was accepted, there should be at least 1 associated offer accepted afterwards. Right? You do not know the data, but believe me, let's say this is the way that this is being expressed. So again, like if you take, let's say, some time to look at this, you will see that it is very natural because we are able to explicitly refer to applications and events using explicit names. So this, let's say, constraint here is expressed here. We can also try to let's say, do this in SQL, or we can try to do this in let's say, Cypher, right? We can look at other languages, and what you see then is that this becomes much more involved. And so the Cypher query looks, I don't know, more compact than the SQL query, but it is incredibly difficult to understand what is really happening here. because there is no real, let's say, usage of the fact that we have these, let's say, event data specific constructs. So this is the usability argument. I hope that you agree that this is a more direct way of expressing this. The other argument is also that if you look at OCPQ, it's much faster, right? So here you see a comparison with Neo4j, SQLite, DuckDB, and OCPQ. And to make comparison fair, so for example, in the SQL queries, we were trying to set the optimal, let's say, indices. We were also, let's say, loading already the database completely into memory to make the comparison as fair as possible. But what you can see is that OCPQ is able to answer, let's say, all of these different questions much faster. Note that this is based on one of the bigger BPI challenge logs, right? So it's something like this is not a small data set, this is a huge data set, but we are able to let's say, respond, let's say, in the order of milliseconds to certain queries. So the reason to use, let's say, this approach is like you can express your queries in a more natural manner. That's one, let's say, big advantage. Another big advantage is that using this technology, also the queries, let's say, can be executed much faster, as long as the data fits into memory, right? Because it has not been optimized, let's say, to cover with the. There have actually been extensions to distribute this over a grid, but that's not something that's being used here. So now it's time to introduce OCPQ, so the Object-Centric Process Querying tool by Aaron Küsters. So let me just, I installed it already, let me just start it. So when you start it, you need to select, let's say, an object-centric event data set. So OCPQ is able to load the different, let's say, formats of the OCL 2.0 standard. So the default standard for, let's say, loading object-centric event data. I load, let's say, a publicly available dataset on order management. I'm using here the JSON load. So the other formats are XML and, let's say, database formats, also graph-based formats. So that's not important. So it gets into the tool. What we now see is that we have 11 event types, right? This is dealing with handling orders, right? So you see activities like pay order, pick item, stuff like that. There are 6 object types, and you also see the, let's say, attributes that they have. So orders have a price, items have a weight, etc., etc. So in total, there are 21,000 events and 10,000 objects, right? So this is a relatively small data set, but not so small that you get an idea of the speed of things. You can explore the data a bit, right? So you can pick a particular object. So let's select this object, and then let's look at the distance, maximal number of neighbors. This is just an exploration tool, and then I can apply it, and you get an ID for the graph-based format, right? So we look at now all the neighbors of this order 990003, and we can see that the squares correspond to let's say, events connected to this order, but you can also see, let's say, the different items, etc. Right? So this is just like a small part of the bigger object-centric event graph. So this to get a feel for the data. Let's now build a query, right? So we can now say, let's throw delete. Let's create a new one. Let's call this demo, right? So we now have, we are now creating a new query. called demo, and we start by let's say clicking on this, and now we can select the different variables. So what we can now do is that we can select object variables. Let's say that O1 is an order. Then we can add another one. Let's say that O2 is not an order, but is an item. We can set event variables, right? So we can say, okay, we have an event called place order, right? We add another event where we say that this event corresponds to, for example, package delivered. Where is it? Package delivered. Yes. So now we set filters, because if we would do this, we would have an explosion of possible combinations, because we would combine any order with any item, with any event place order, with any event package delivered. And of course, we are interested in relationships between them. So for example, we are interested that the orders and the items are actually related through an O2O relationship. There's a possibility to qualify the relationship if there are multiple qualifiers, but that is not relevant here. Now we look at orders and items that are connected to each other. Of course, we still need to connect E1 to O1, right? And that's an E to O relationship. So E1 and O1 need to be connected. And we need to connect package delivered to the item. So O2 and E2 need to be related. O2 and E2 need to be related. So I do this, and now I can push this run button. And what we now see, I can also make this bigger. So what we now see is that there are like if we look at the combinations of O1 and O2, there are almost 8,000 combinations. Because for every item there is just a single order, this is exactly the number of items that exist there. We can always click on this, and then we can kind of walk through, let's say, all the different things. And if this is a bit overwhelming for you, I would highly recommend taking a look and really inspecting let's say the rows in the tables that we are doing, because they are showing the combinations of bindings. So these are orders and items that are related to it, and E1 is always related to O1, and E2 is always related to O2. So this is what we have created now, and now we can, for example, add a constraint, and we can, for example, have a constraint related to time. So we have two events, E1 and E2. So E1 was placing the order, E2 was the delivery. And we can, for example, say that we want this to happen within 2 weeks, right? So I now say the time between E1 and E2 is between -infinity and 2 weeks. And if we add that, right, and we run this, then we can see that this does not always happen, right? And if you now look at the table, you see, let's say now in total it's a small percentage, but now in this last column you can see where the violations are. I can also click on this, and now we see all the let's say almost 1,000 items that have this problem, right? So they to deliver them did not happen within 2 weeks, right? So we have a violation of 12% approximately. So this is showing, let's say, if we are just using a single schema, right? And what we can now do is that we can start combining things, right? To keep things understandable, I will delete, let's say, some of the things. Right, so I delete this row, I delete this. Then of course I need to remove this constraint, and I need to remove this constraint because they don't exist anymore. And I I delete also this one, right? So if I now run this again, right now there is no constraint, so it also doesn't have a color. But I forgot to say, if there are just a few, let's say, violations, the color is green. If the violations is increasing, the color is changing, so that in one glance you can see where the problems are. So after doing this, I can add, for example, another let's say of these schemas, and I can connect them. And if I'm connecting them, that basically means that I'm making all the combinations, right? So now I can create here an O2 based on items, right? So now we have orders here and items here, and now I can do the same thing, right? I can now create an E2 of event type, for example, package delivered, as I did earlier, but now it is distributed over to schemas. Of course, I need to relate them, right? So what we see is that there is still an O2O relationship between these two, right? So orders and items need to be related. And I need to do an E2O, right? So E2 is related to O2. So I've now split kind of what I first put into one schema into two schemas, right? And they don't have to have a name, but I always like that the relationship is actually, let's say, named. So what we now have is that we now see that we have here the orders and we have here the items connected to these orders, right? So if I now run this again, it is kind of what you hopefully expected. So now here we have 2000 rows just talking about O1 and E1, right? The order and the place order event. So that is what you find here. If I now look here, there are 8000, right? So for every item we have here. So what you now see is like this context that you see above is implicitly included, right? So if I look at these almost 8000 rows, they also refer to O1 and E1 because that has been inherited from there. In this lower part, again, I could now add like the constraint that I added before. But for example, now I show that we can, so now every order is in this way connected to items. And now I can set a filter, right? That I can say that, so now I look at the child binding set size. So it was called A. So now we want to filter it that we are interested in all the orders that have at least 3 items in them, right? So now A is bigger than 3. So we are now interested in the orders that have at least 3 items in it. Note that this number, we now have 2000 orders, 8000 items. And if I now filter this, right, what you see is that this went down from 2000 to 1481, right? So we are restricting it here to, let's say, all of these, let's say, orders that have at least 3 items in it. Also, what you see is that the number of items went down, right? Because this connection, like there needs to be a parent on the other side. So we have lost a few items, and these are the items that are in orders that had, let's say, 2 or less items in it. So this is showing how you can use this as a kind of filter. So what we have now specified, we are interested in all the orders that like have at least 3 activities. Let's now extend this a bit to also include, let's say, a constraint in this way. So let me now add this. So we now make this connection. Let's call this connection B. And what we now do is that again we add let's say an item, right? Because that's the part that hopefully you're now a bit familiar with. Now we can look at event variables, like let's take here item out of stock, right? And of course we should first connect this again. So we have an O to O relationship between these two, and we have an E2O relationship between E2 and O2, right? So I've connected O2 to the top, I've connected E2 there. So if we now run it again, so this is constrained by all the orders having at least 3 items, right? That's based on this part. And of these orders, we navigate to all the items, and in total there are let's say 1400 items for which there is an item out of stock event, right? That's what we have. And now let's add here a constraint. The example is not super meaningful, but I just want to show the different capabilities. So again, we can talk about the child binding size. I think something went wrong. Yeah. So now we can select B, right? So we are interested now in, let's see whether that exists. Right, so now we are interested in orders that where the B set of children is at least 2, right? So we are now looking at orders where there were 2 items that had an out of stock situation. That's a constraint, right? And that's a bit unusual. If I would say this is a constraint, I think it's better to reverse it, that the maximal count is 2. Otherwise, it would not make a lot of sense as a constraint. Right, so now we look at all the orders that have at least 3 items in them that had a package delivered. And on this side, like we are looking at the item out of stock ones, and there should be less than 2. And if I now run it, what you can see is that there are 83, let's say, instances, so rows in this table, which are violating this constraint, right? So it's not affecting the numbers here, but now we can see the violations, and again, we can drill down, let's say, on the, orders that have precisely this problem. So I hope that this explains you a bit, let's say, how this works. If you paid attention, then you could see that if I look under filters, for example, there is a whole range of other things that I did not explain. There's also a kind of scripting language to describe these types of things for very, let's say, advanced queries. The same if you look under constraints, kind of you can see the almost the same set of things, but there are also logical connectors that you can use there. As of course, if you want to formulate a constraint, these are things that you can add. You can also add connector gates connecting these things, I think, but that all goes too far. So why is this relevant? This is relevant because querying of object-centric event data is something that is very tricky, very difficult, much more difficult than if you're looking at case-centric data, where all the thinking in a way has been done before loading the system, although the view may be distorted. This is a topic that is, so to make this usable is a challenge. And also from a performance point of view, like experiments show that if you have a dedicated query engine to do these types of queries, you can be, like orders of magnitude faster than if you're using simple SQL queries or something similar. I hope this encouraged you to download OCPQ. And again, credits go to Aaron Küsters, who developed this very interesting tool. So I hope that this gave some insights how to get humans in the loop. And so for querying, if people are using process mining, that's what they spend most on the time on, right? If they want to investigate a particular problem, right, you need to write these queries, and most users are unable to do so, right? So it's pre-packaged in dashboards. But to create these dashboards, you also need to use these querying languages. Using query languages is something that's very important and very time-consuming. So that was one element. The other element was like while modeling, while doing conformance checking, let's say it's very important to look at this interaction, human in the loop. So the overarching theme is, let's say, how to keep humans in the loop while doing process mining, either in the phases where you are preparing the data, in the phases where you are investigating a problem, but also in the phases where you are discovering a reference model, right? Or you want to investigate cases that are deviating from some, let's say, predefined model. As mentioned, Cortado is a tool that is still based on case-centric event data. OCPQ is based on, let's say, object-centric event data. Of course, in the future, it would be nice to look at solutions where, let's say, both of these, let's say, ideas are being combined to do, let's say, not just querying, but also discovery of object-centric process models in a much more interactive way than that we do today. Because today we set parameters and then suddenly there is a model that is often not satisfactory, and it is very important to give the user more control over discovery to get the insights that he or she wants. Thank you very much.